Hi everyone, thank you for being here. Today I'll be discussing resolution of double salts via crystallization-induced diastereomeric transformation, solubility and catalyst effects. This talk will explore how CIDT can be leveraged as a powerful technique for resolving double salts with a focus on the role of solubility and catalyst influences in optimizing selectivity. Let's dive in. My name is Melba and I have a PhD in chemical engineering. I work as Innovation Program Manager, where I lead strategic collaborations and technical initiatives, particularly in small molecule projects. Before diving into the details, let me give you an overview of my talk. I will start with a brief introduction to APC, followed by our motivation behind this study. Then I'll walk you through our experimental findings, highlighting key observations on solubility and catalyst effects. And finally, I'll wrap up with a conclusion. At the Medicine Accelerator, our mission is to accelerate the delivery of quality, life-changing medicines to patients. We are a digitally led R&D and GMP ecosystem that transform how medicines are researched, digitalized, and manufactured. At its core, this disruption is facilitated by three interwoven strategic elements. Best-in-class science, advancing the boundaries of pharmaceutical process, research and development through a world-class team of scientific experts. First-in-class digital, accelerating medicine development and manufacturing outcomes through the application of our state-of-the-art digital technologies and artificial intelligence. Science-first GMP, manufacturing, driving manufacturing outcomes through industry-first scientific and digitalization breakthroughs. Over 50% of the active pharmaceutical ingredient possess a chiral center. These chiral molecules exhibit as enantiomers, which are non-superimposable mirror images of each other. Despite identical chemical compositions, enantiomers can exhibit distinct biological activities due to their differing three-dimensional configurations. Consequently, the production of enantiomerically pure drug substances is highly desirable to enhance therapeutic efficacy and/or mitigate potential toxicological side effects. Chiral compounds can exist in three main solid-state forms: conglomerates, racemic compounds, and solid solutions. Among these, over 89% of active pharmaceutical ingredients are found to crystallize as racemic compounds, where enantiomers are present in a 1:1 ratio within the crystal lattice. In this study, we focus on Ketoprofen, a racemic compound, and investigate its resolution via crystallization-induced diastereomeric salt transformation. Ketoprofen is a non-steroidal anti-inflammatory drug that exhibits chiral properties. Its S-enantiomer is primarily responsible for its therapeutic effects, including reducing inflammation and alleviating pain. On the other hand, the R enantiomer has been explored as a potential additive in toothpaste formulation due to its analgesic properties. Through this study, we aim to better understand the resolution of ketoprofen. Diastereomeric salt crystallization is a classical resolution technique that involves using mixtures of resolving agents to selectively form diastereomeric salts. A racemic compound reacts with a chiral resolving agent to form diastereomeric salts, which can then be separated based on their solubility. The key properties of diastereomeric salts are asymmetry. The salts are non-mirror images and have different physical properties. Distinct morphology. They exhibit unique crystal structures and different solubility. This difference enables selective crystallization. The maximum resolution yield in a diastereomeric salt crystallization process is 50%, as only one of the two enantiomers can be selectively crystallized. The diastereomeric salts can crystallize in different forms, including simple eutectic, a system where both salts crystallize separately; double salt, a stoichiometric combination of both diastereomers in a single lattice; Mixed crystals or solid solution, a homogeneous mixture where the two salts are incorporated within the same crystal lattice. The formation of a simple eutectic system is often associated with a more straightforward resolution process. However, resolution of a double salt or mixed salt has proven to be challenging. In this study, ketoprofen is reacted with phenylethylamine to form diastereomeric salts. S-ketoprofen S-phenylethylamine, referred to as P-salt, R-ketoprofen S-phenylethylamine, referred to as N-salt. From this point forward, I'll refer to them simply as P-salt and N-salt for clarity. Outer excited analysis was performed to examine the solid-state structure of the P-salt, N-salt, and their mixtures. The excited pattern of the pure P-salt closely matches with the p-excited pattern of the single crystal P-salt, as previously reported by Rossi et al. When analyzing the salt mixtures, new diffraction peaks appear that are not present in the individual P-salt or the N-salt patterns. The presence of these additional peaks indicates the formation of a double salt or mixed salt system, rather than a simple eutectic mixture. These results provide solid-state evidence supporting the formation of a new crystalline phase in the salt mixture, highlighting the complex nature of the crystallization process. In this study, DSE is used to analyze the melting behavior of the pure P-salt and N-salt and also their mixtures. The key properties measured are the melting temperatures of the pure P-salt and N-salts, the lowest melting point observed in the system indicating the composition at which both salts co-melt. By analyzing the DSE thermograms, we can distinguish different solid-state interactions in the system. Onset of the first melting peak represents the temperature at which melting begins, often linked to the eutectic transition. Peak or end of the second melting peak indicates the final melting phase corresponding to the more stable diastereomeric salt. These thermal properties help us understand the solid-state interactions and determine the feasibility of selective crystallization for resolving ketoprofen. In this study, we analyzed the solidus and liquidus lines to characterize the phase behavior of the salts. Solidus line defined as the onset of the first melting peak in DSE, marking the transition where melting begins. Liquidus line identified as the peak or the end of the second melting peak, indicating the completion of the melting. To predict the liquidus curve and understand the solid-liquid equilibrium, we apply Schroeder-Van Laar equation, which is equation 1, used for describing the melting behavior of the solid solutions and eutectic mixture. Prigogine-Defay equation, equation 2, applied to account for deviations from ideal solubility and phase interactions in multi-component systems. These thermodynamic models help determine whether the system forms a double salt or mixed salt, providing crucial insights into the crystallization behavior of ketoprofen salts. Ketoprofen exhibits key properties of diastereomeric salts, including asymmetry. The two diastereomeric salts have distinct structural and solubility characteristics. Multiple eutectic composition. The presence of two eutectic points suggests the formation of a double salt rather than a simple eutectic mixture. The eutectic compositions are observed between 40 to 52% P-salt. These findings, supported by the DSE and XRD, reinforce that ketoprofen and phenylethylamine crystallize as a complex double salt. To guide solvent selection for crystallization process, a computational solubility screen was conducted using Cosmotherm for a range of pure and binary solvent mixtures. 33 green solvents were initially screened based on the DSE data at 25 and 50 degrees Celsius, employing Cosmo RS for pure P-salt. Of the 30 solvents screened, 6 were selected for experimental validation: THF methyl acetate, 1-butanol, 2-propanol, butanol, ethyl acetate, ethanol, and acetonitrile. These solvents were chosen based on the following criteria: low solubility at 25 degrees Celsius and higher solubility at 50 degrees Celsius, ensuring sufficient yield and throughput for potential crystallization process. Based on the experimental results, a solvent system composed of 2-propanol and heptane in a 50-50 weight ratio was determined to be the most suitable solvent mixture. The ternary phase diagram offers critical insights for the design and optimization of enantiomer separation. Experimental data presented in this figure indicates that the P salt exhibits slightly lower solubility than the N salt. Across the investigated temperature range, isothermal solubility studies, where the starting composition is 50-50, consistently gave the highest solubility at 57 weight% P salt. In contrast, the polythermal solubility studies revealed that the composition with 31 weight% P salt exhibited the highest solubility. Isothermal crystallization experiments were performed based on these results and consistently gave a low purity of P salt, which was less than 55 weight% P salt. To address the challenges of purity, an alternative approach was investigated, initiating recrystallization with a P salt enriched solution and heavy seeding. While this demonstrated improvements in purity, it proved economically unfeasible, limiting its practical utility. Consequently, this approach does not present a viable pathway for P salt crystallization. Crystallization-induced diastereomer transformation is a methodology that integrates crystallization with in situ epimerization, often driven by thermodynamic control. This approach enables the selective convergence of a mixture of diastereomers or diastereomeric salts into a single diastereomeric form through processes such as base-catalyzed epimerization. CIDT is known to be feasible when diastereomeric salts crystallize as a simple eutectic mixture. The following is the workflow of this process. The catalyst facilitates protonation or deprotonation at the stereocenter, promoting epimerization between the diastereomeric salts. The selection of counterions influences the equilibrium between stereoisomers, controlling the formation of diastereomeric salts. As equilibrium shifts, the preferential crystallization occurs, typically favoring the less soluble diastereomeric salt. The less soluble salt is isolated from the solution, allowing for purification. In the initial study employing 7 different base catalysts, it was observed that the CIDT was feasible using DBU as the base catalyst. The other base catalysts yielded crystals with a P salt purity of less than 59%. In contrast, the use of DBU as the base catalyst resulted in final crystals with a significantly higher purity of 79%. Consequently, DBU was selected as the base catalyst for further optimization studies. The CIDT process was further optimized in a solvent system of IPA heptane 50-50 weight% and at different DBU concentrations. DBU with its high pKa proves to be the most effective base for epimerization as it provides strong basicity and steric selectivity, ensuring effective deprotonation of ketoprofen and subsequent salt formation with phenylethylamine. The table below presents the impact of different concentrations of the base catalyst DBU on purity and yield of P salt. It is observed that increasing the DBU concentration influenced both the purity of the final solid and also the yield. To understand the role of DBU in the process and its impact on yield loss, solubility studies were conducted across different DBU concentrations. These findings highlight DBU's dual role as a catalyst and co-solvent in the process, where its concentration significantly impacts the solubility of the P salt. The reduction in solubility temperature with higher DBU concentration may contribute to the yield loss by enhancing solubility and reducing recovery of the elevated DBU levels. To conclude, This study has successfully demonstrated the feasibility of CIDT for the resolution of double salts. The solubility phase diagram confirmed double salt in 2-propanol heptane solvent system. Among the catalysts evaluated, DBU was found to be the most efficient promoter of epimerization at room temperature. Further optimization revealed that DBU concentration of 5 mol% achieved a purity of 98.8% P-salt with a yield of 26.2%. This represents a significant improvement as crystallization of pure P-salt was challenging. The findings highlight DBU's dual role as a catalyst and co-solvent influencing solubility and yield. These results indicate the valuable insights for optimizing CIDT process and offer a scalable approach to enantiomer separation of diastereomeric salts for pharmaceutical applications. I sincerely appreciate my incredible team for the dedication, hard work, and support throughout this project. Thank you for your time and attention.